All right, so on the board, I have kind of the major topics of this unit listed. So fluids is broken into kind of three chunks. 3.5, 4, kind of how you want to break Bernoulli's here. But it's pressure, density, pressure, depth. There was a worksheet called that. Buoyancy, flow rate, which is what we're starting today, and then kind of an extension of flow rate is Bernoulli's principle. So it's kind of be aware of that. When we talk about pressure, density, pressure, depth, there was calculations like pressure is force divided by area, rearrange that, solve for a different variable. Density is mass divided by volume, solve for mass. We do that a lot with buoyancy. Solve for volume when we could. And then pressure or depth is plugging numbers into the equation, that one pressure or depth equation, and solving for how much pressure the deeper you go in a fluid. When we talk about buoyancy, there's a couple main types of buoyancy problems and calculations that we've done, and they kind of mimic the progress quiz ones that we've done. There's like how far underwater is something that floats. How much stuff can that thing hold? And that how much stuff could also be like how many, like the pennies. How many pennies can your boat hold? How many penguins could that iceberg hold? We did an in-class penguin problem. We did a lab. We did a progress quiz. Shouldn't be a shock to see something like that. And then for buoyancy, the other kind of big one was, well, I guess there's two. It was kind of a balloon, and then it was with a string like you're holding something else. So we have some tension in the string. We're going to start talking about flow rate today, and like I said, kind of a subsection of flow rate is this thing called Bernoulli's. So we're getting close. We're not done yet, but we're getting close. So next week we'll be testing it at some point. I'll try to figure out, give you a better idea as to when. But, so flow rate doesn't have a fancy variable. Sometimes students choose to abbreviate it FR for flow rate, and I'll probably do it today because I'd rather write FR than flow rate, but there's not a formal variable for it, just so you're aware of that. And on your formula sheet, it's listed in fluids right here. Flow rate is equal to, and then there's two different things. And it says flow rate is equal to A times V, and it says it's equal to vol divided by T. So realize that there's really two formulas there. We could say flow rate is equal to A times V, or we could say flow rate is equal to volume divided by time. So depending upon the information given depends upon which flow rate equation you're going to want to use. Now most of the time when we talk about fluids flowing, we're going to be talking about water flowing. Now what does water flow through? Well, lots of different things. Hoses, pipes, rivers, streams, waterfalls. I don't know, those are the big ones. But this could be any fluid. So most of you have what we call forced air furnaces at your home, which basically means you have these heat vents on the floor that when your furnace kicks in, it blows air, forcing air out of the vents. Those ducts, or those vents, well, the ducts, are basically like pipes. They're just rectangular in shape. They aren't watertight, they blow air. But it's flowing, pushing the fluid, air, warm air, throughout your house to heat your house. Or in the summer to cool with air conditioning. So it doesn't have to be water, but that's often what we reference. So when we talk about volume, the best units, the preferred units that we use are going to be cubic meters. Okay? This is going to be kind of the preferred one. Now remember when I had that cube on the back table, 1 meter by 1 meter by 1 meter, that would hold about 264 gallons worth of water. It was like 2,200 pounds worth of water it holds. So that's 1 cubic meter. So 1 cubic meter is really big. And when we talk about like water flowing through a pipe, this pipe is not very close to 1 cubic meter. Well, not cubic meter. This would be a square meter, right? But if we talk about 3 tiles by 3 tiles, that's 1 meter. This is not very close to 1 square meter either. So we often are talking about water flowing through a pipe, but in order to fill like that cube, that's a lot of water. So if I had water flowing out of this pipe, that water would have to flow out of this pipe probably for quite some time to fill that cube, assuming it's size it. Because that'd be like 200 some gallons worth. So cubic meters is a big volume of water. It's kind of our preferred, but it doesn't have to. It could be cubic feet. It could be liters. It could be gallons. It could be milliliters. It could be fluid ounces. It could be lots of things. This is our preferred one, but it's not necessarily a for certain one. So just kind of keep an eye on your units. For time, our preferred unit is still going to be a second, but this could be per minute, this could be per hour, this could be per flush as a unit of time. It's an event, it's an occurrence. And the reason why I'm mentioning that is because toilets, they measure the flow rate of a toilet, and it's how much, kind of a flow rate, is how much water goes down the toilet every time you flush it. It's a flow rate. Typically it's measured in liters per flush or gallons per flush. So sometimes if you see on toilets, you sometimes see like a number with LPF or GPF. That's what that's representing. Every time you flush the toilet, how much water goes down. So we aren't going to deal with per flushes, but realize you could. But our seconds is going to be our preferred unit of time. But we don't always use per second. Shower heads, for example, have a flow rate. When you buy a shower head, there's a certain flow rate that the government requires it meets. It has to be at 2.5 gallons per minute or less at some pressure, 80 psi, 78 psi. Otherwise, we're wasting water. We're using what they consider to be too much water. So that's gallons divided by minutes, the gallons per minute. Okay, if we're talking about water flowing through a river, well then maybe it would be gallons per second, or gallons per hour, or gallons per whatever. So just kind of be mindful of what units you use, and then this is simply a division to give you your units for flow rate. Our preferred unit for flow rate is meters cubed per second, because that'd be meters cubed divided by seconds would be meters cubed per second. But it's really lots of combinations. What the units you use are the units you get back out. So if I use gallons per minute, I take the number of gallons and I divide by minutes, then my units would be gallons per minute. If I went the other way and I used gallons per minute, and my time was measured in minutes, then my volume would come out in gallons. So just something to keep in mind. We're going to use this a lot, but there are some exceptions to it. But that's most common what we're going to use. The other part of this equation, or the other equation, because like I said, there's really two different equations here, is we could say flow rate is equal to A times V, where A represents area, and that area is measured in meters squared. And V represents velocity, and that's in meters per second. Now, those are the units that we will use for area, and those are the units we will use for velocity. Now, if you take meters and you multiply by meters per second, meters squared, and you multiply by meters per second, then this is the unit we get out. We get meters cubed per second. So that cubic meters per second, remember, this isn't very close to 1 square meter, so my areas tend to be pretty small. And if I'm talking about how many of those, how many 260 some gallon tanks can I fill every second, that's not, it's gonna be a small number, right? We don't fill 60 some gallons per second with most applications. Maybe a river does, but we don't. When we talk about flow rates through like ducts or your heating system, that might be cubic CFMs, cubic feet per minute, CFM, cubic feet per minute, CFM. Okay, it's just a different measurement of volume, and it's using minutes per second. How much air is coming through your heating system? How fast is it moving your air? Okay. So when we talk about flow rate, we'll start with this in terms of water in a pipe, and we'll talk about water. We'll talk about water in a sink. Okay, so if I turn on my sink and I attach this hose just so I can kind of direct it a little bit, we have water coming out, and if I turn the water up, more water comes out. If I turn it down, less water comes out. So we can go through and we can determine flow rate. So this beaker is 1 liter right here. And we could go through and we could time very precisely how long it takes to fill this 1 liter beaker. And we can go 1, 1,000, 2, 1,000, 3, 1,004, 1,005, 1,006, 1,007, 1,008, 1,000. Hey, look at that, 8 1,000. So it's at 1 liter. My volume is 1 liter per 8 seconds. We could do that math and we'd get some decimal. Okay? But if I change the flow rate, okay, we can go 1, 1,000, 2, 1,000, 3, 1,004, 1,005, 1,006, 1,000, sure, 6. Look, it said 6. Okay, so it had a different amount of water coming out in that amount of time. Now we could go the extreme the other way, and we could time how long it would take with that. But we're not going to do that. Okay, now we could do the opposite. If I know my flow rate, okay, and if I know my flow rate is 1 liter per 5 seconds, how long would it take to fill 2 of these? 2 liters, right? So if we knew our flow rate equals, okay, and if I have a 2 liter volume, I could go through and I could calculate the other one. Okay, so there's different ways we can do it, and that's the one we're going to start by talking about, is what if we are talking about volume divided by time. So, volume divided by time is how we're going to start. So, I have So let's take a look at this. So on your sheet, there's a couple things. And at the very top of this, there is the equations for flow rate. And I have this flow rate listed separately. I have flow rate is equal to A times V, which is what I have right here, is A times V. And then below it, I have area is equal to volume divided by time as a separate formula. But here I wrote it as the same. It's really right, you just got to pick which one you know the information for, and then you choose the right one. There's also some other things like, hey, the area of a circle is pi r squared. There are some conversion factors that we may or may not need. 1 milliliter is equal to 1 times 10 to the minus 6 cubic meters. That was a calculation we did in the conversion we did in your penny boat lab. And 1 cubic meter, that 1 meter by 1 meter by 1 meter is 264.172 gallons. So there's some conversion factors if we need them. Okay, but if we take a look at number 1, it says a pipe. Oops, I actually don't want to do number 1. I want to start with, sorry, wrong one. I want to start with number 2. So problem number 2 says if a 0.05 cubic meter container fills in 4.2 seconds, what is the flow rate of the water? So we have two formulas. We could say flow rate is equal to A times V, or we could say flow rate is equal to volume divided by time. And in this particular question, it's asking for flow rate. We're asking to solve for flow rate. Which one's going to be more useful, the volume divided by time or the area times velocity? So what's 0.05 cubic meters a measure of?
Volume.
That's a volume, right? So volume is equal to 0.05 cubic meters. And it says it fills that container in 4.2 seconds, which is a time. So then the flow rate is equal to volume divided by time is going to be the one that we want to make sure we use. So flow rate is what we're solving for. So again, I'm just going to abbreviate FR, is equal to our total volume of 0.05 divided by 4.2, and we're going to calculate the flow rate. Now this is cubic meters divided by seconds, so my answer is going to be in cubic meters per second. So if we take 0.05 and we divide by 4.2, we get 0.012 cubic meters per second. That's our flow rate. And we calculated the flow rate much like I did with my beaker in the back. I knew the volume. I timed how long it took to fill it to that volume. And then we could go through and we could calculate the flow rate. Okay. If we take a look at question number 3, question number 3 says that the flow rate of a hose is 0.04 cubic meters per second. How long would it take to fill a 0.3 cubic meter bucket? Try that one. Similar calculation, but this time it's asking for not flow rate, it's asking for you to calculate how long would it take. So those are the variables that were given. They gave us a flow rate. They gave us the volume. Units are important, right? Cubic meters is a volume. Cubic meters per second is a flow rate. Now I think that one very specifically says the flow rate is. And it's saying how long, so we're calculating time. Same starting equation, it's the flow rate is equal to volume divided by time. And it looks something like that. And then when we do our cross multiplication and division, we get a time of 7.5 seconds. Now, that's one way we can calculate flow rate. We can collect how much water, and then we can time how long it takes to fill it. That's easier to do sometimes than others. For example, relatively easily in a sink, relatively easy to do under a shower, right? If your shower head says it's 2.5 gallons per minute, you could take a 5-gallon bucket, stick it underneath the shower head for 1 minute, and then you could measure it, right? And do you really have 2.5 gallons? Or you could go the other way and say, well, what is my flow rate? I could measure how much water comes out of my shower head in a minute, or I could do it in 30 seconds, or I could do it in 10 seconds if I wanted to, and I could get that per minute or per second. So that's one way we could do it. Now, it's really hard to do that, say, in the Wisconsin River, or the Mississippi, or the Eau Claire River for that matter, or the little tiny ditch outside your house that has water flowing, but you really want to know how much water is flowing through that ditch. That's a harder calculation to collect all the water flowing out of the Wisconsin River and say, hey, at this portion right by the Domtar Dam, how much water? Now, actually, the Domtar Dam, we maybe could kind of do it based upon, they only let X amount of water at certain heights, and we could do some calculations that way. But the other way we can calculate it is with the other part of this flow rate, where we can say flow rate is equal to area times velocity. So, in 9th grade, you did, I don't remember exactly what they called it, but it was the day of the river field trip, where you went to a couple different places. You did some canoeing, you did the old school forest, the Eau Claire River site, they call it. You did, I think you went on a dam tour, or you looked at a dam, I don't remember what you did. You did something, right? So then, my students in the past have told me, have a good day. Thanks. You went through and you did something that you did a river profile. So the idea, and maybe you didn't know it by this name, but in math class you probably did it, and you have your river. And what you do is you walk along with a stick, and you basically measure the depth of that water at different locations, and the idea is you go through and you get all these different depths. Then you make some assumptions based upon some relatively basic shapes, and what you can do is called a profile, but basically you can determine the cross-sectional area of the river. Okay, you could go through and you could determine what's the area of the river, the cross-section. Now, a cross-section is like this pipe. We take a pipe and I chop it, and if I look at the cross-section, this is what we're talking about, right? So if this is your river, and if I were to look at the river from the end, this is what we'd see from a cross-section. Okay, so the cross-sectional view of my river would be like looking through my pipe, and we could get our river profile. So once you determine your area, then all you would have to do is calculate the velocity of your river, and then you should be able to get an approximate flow rate of the river. So typically the way a science class would do this is they go through and they take their measurements, and then they take a tennis ball, or something similar, rubber ducks work nice too, and you start you yell on, hey, you ready? Yeah, we're ready. And okay, 1, 2, 3, and you drop the rubber duck or the tennis ball, and they start a stopwatch. And then the tennis ball floats, or the rubber duck floats down the river for some predetermined distance, and then stop. And then, wow, you know there's a known distance, you calculate, you can time it, you can calculate then our velocity, which then we can determine the flow rate of the river. Now, it's not perfect because the surface velocity might be different than down a little bit, right near the bottom. There's some differences in speed. Sometimes they talk about undercurrents and all that stuff. So it's not perfect, but it's a pretty good approximation. There's also people who keep an eye on these, especially whitewater rapids people, whether they're a rafter or a kayaker, because they want certain flow rates through the rivers for their paddling to be fun. right? If you're gonna go whitewater rafting through rapids, but there's not enough water, it's not really a rapids, it's just like a lazy river. So there's these things called gauge stations that they can go through and they can measure some of this stuff. So that's the other way is we can go area times velocity, and pipes is a pretty common thing that we go through and measure flow rate with. So a pipe, when we talk about a pipe, there's my pipe, it has a certain radius that has some volume. So if we take a look at question number 1, it says a pipe with a radius of 0.02 meters. Okay, so if I have a radius with a pipe with a radius of 0.02 meters, that's like 2 centimeters, and it has water flowing through it at a velocity of 1.2 meters per second. What is the flow rate? Okay, so it's asking for a flow rate. Well, we have two equations for a flow rate. We have flow rate is equal to A times B, or we have flow rate is equal to volume divided by time. Given the information that we have, volume divided by time isn't going to be very good because we don't have a ton. So ultimately we're going to want to say, hey, flow rate is equal to A times B. That's where we're headed. However, the area of this pipe wasn't given, the radius of this pipe was given. So this pipe is a 2-inch pipe. So 2.54 centimeters is about an inch, or 2.54 centimeters is 1 inch. So this is about the pipe we're talking about right here. So it's about 2 centimeters in radius, so it'd be about 4 centimeters in diameter. You know, a little bit too small. But if we had water flowing through it, we can determine what we would call the cross-sectional area. So what is this area inside the pipe that the water is flowing through? That's what we refer to as a cross-section area. So it's a circle, right? Most pipes are circles. You could say, well, what pipe is it? Your furnace ducts? But you could say, but that's not really a pipe. You're right, it's not, it's a duct. But it's a rectangular pipe-ish thing. Aqueducts, those aren't circles, but they aren't pipes. So but for when we talk about pipes, the area is pi times radius squared. And we have to have our units in meters, my radius in meters, in order to get my area in meters squared. So pi is equal, area is equal to pi times 0.02 squared. And then our area and I don't use 3.14, I hit the pi button on my calculator. And for these, we want to try to not round whenever possible. Using all the digits, storing those numbers in our calculator is going to be beneficial, because if we start rounding now, the more times we use a rounded number, the more inaccurate our number gets. Okay, so the area of my pipe is 0.012566637. So I hit store in my calculator. Now we can go through and we can say, well, my flow rate is equal to that area that was just calculated, and I write down the digits that I have on a board, but I'm going to use I'm going to use all the ones that I have, many more than the 3 digits. So then I can, since it's still my calculator, I can just hit times, and it will take that previous answer, and we can get a flow rate that's equal to 0.00151 cubic meters per second. Now, it's a little bit unfortunate that our preferred units in physics for flow rate is cubic meters per second, because that's a really small number, and it honestly doesn't mean very much to us. But we could then take that and say, well, if that's my flow rate, how many seconds would it take to fill 1 cubic meter? You know, 1 meter by 1 meter by 1 meter. and then we put. So these numbers are typically small. Be aware of that these numbers are typically pretty small because remember, 1 cubic meter, it's a lot of water. Okay, it's 200 and some gallons. So how much water would have to come out of this pipe every second to fill that liter, that 1 by 1 by 1 in a pretty quick time? It'd have to be a lot. So these numbers tend to be on the smaller side, so just so you know. Okay, why don't you try problem number 4? Okay, so problem number 4 is similar to problem number 1, except for it's solving for a different variable. So why don't you try number 4? If a 0.01 meter radius pipe has a flow rate of 0.002 cubic meters per second, how fast is the water flowing through that pipe? So why don't you try number 4? Okay, so gives us a radius, which is okay, but we need area. So we got to take pi times our radius squared to give us our area, and 0.000314, da 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 da. The flow rate was given at 0.002. My flow rate, oops, I missed a 0. Okay, so we have our flow rate, we have our area, we solve for V, and V ends up being 6.36 meters per second. Okay, so if we know the flow rate, we know a radius, which then can give us our area, we could then calculate how fast the water moving through the pipe is, or downstream is, or whatever. Okay. So if we know those, we can go through and we can look at those things. Now, slight kind of variation to this is if we go back to my amazing example of filling a beaker full of water. Okay, and if I fill a beaker of water, and I'm only going to fill it to 500 this time. Okay, so if I go through, and if I time how long this takes, 1001, 1002, 1003, 1004, 1005, 1006, 1006 and a quarter. We'll go 6 and a quarter, okay, ish. Okay, it took about 6 seconds to fill that beaker. Now, I'm not going to change the faucet. The amount of water flowing out should be the exact same. Now, let's think about this. Let's pretend that this is the only water running in the entire building, which is very unlikely that no one somewhere is running any water. But let's just pretend for a second. Do you think the water coming from the Village of Weston through a pipe is as big as the hose that this water is coming out of? No, right? I don't know how big the water main with the pipe coming into the high school is, but it's probably a lot bigger than this pipe. In a typical house, it's either like 1 inch, 3/4 inch, kind of depends, but generally about 1 inch in diameter. This is only about, I think this is like 3/8. Okay, so in a school which has lots and lots of water use, they're going to probably run a bigger water main. Now, running down the street is going to be even a bigger water pipe. However big that is, I don't really know, but it's a plastic pipe. 6 inches, about 6 inches will go up. Okay, so it's about this big, and then they run a line, that's your main, that they run into your house, or they run into the school. But let's pretend for just 1 second that this was the only water running in the entire building. So let's say we have a water pipe running down the street, and we're the only ones on the street, not very likely, that's running water. Okay, what's true about the amount of water flowing out of here compared to that's flowing through this pipe? That's this big. Is there more water flowing through this pipe, less water flowing through this pipe, or this much water flowing through the pipe if it's the only thing connected to that pipe and has water running? Same, right? Okay, so if we have this giant water pipe main and there's water in the pipe, is the water moving through that giant pipe very fast for this much water? No, but it's moving, right? It's pushing, it's moving down the line. So it's kind of, the idea is the amount of water flowing is going to be the same. Now, what happens if I take this and I say, well, how far away from my sink can I get? I can get about that far away, okay? Now, why can I go that far away? It's a projectile, horizontal launch, 2D motion problem, and because of the velocity that's coming out of the hose, it can get X many meters away. Now, how could I get further away from my sink? I could what? I could turn the water up, true, and then I would have more flow rate, right? I have more water flowing. Or I could what? Lift it, yeah, that's good. I can lift it higher. That's not what I was thinking, but yeah, absolutely. Or you ever like water your flowers and your little brother who's been bugging you for a while comes by and like, you can't get me, because they're just like that far away, but you can get them. How can you get them? Right? You can go like that. Now try not to spray any of you, right? You can go faster. Now, if I change, right? Is that water coming out faster or slower than it did before? Speed-wise, faster, right? Now let's, what was it, 6 1/4-ish to go to 500. Let's see how fast we can go this. 1001, 1002, 1003, 1004, 1005, 1006. Pretty close. Okay, no, my precision timing is not the best. But I didn't turn this, but it's close. I mean, it's not perfect. But the amount of water coming out of my hose now versus now is the same amount of water. Okay? It's the same thing with like this syringe. If I fill this syringe full of water And if I push on this syringe, then what we have is we have this plunger that moves. And this plunger, I'll go this way for the camera. With this plunger, okay, it has a certain speed. And if we were to go through and we were to time how long it takes to go some distance, I could determine the velocity of that plunger. And I could figure out, well, what's my cross-sectional area of that plunger? And I could even calculate, there's this volume over here, and it talks about like cc's, or ounces, and I could go, well, I could, from 35, cc's to 25 cc's, cubic centimeters, I could say, well, how long does it take, how much water is going to go up per unit time? I can figure out a flow rate. But what's true about the amount of water flowing through the syringe, this part, versus the water coming out of this part? Let's just pretend I had a gallon per minute coming out here. How much water is coming out here? Where else can this, if we have a gallon of water flowing right here, which is way too much for the record, where's the only place that water can go? That way. So if we have a gallon per minute going here, then how much water do we have going that way? A gallon per minute, right? So the idea that I'm trying to point out is even if we change the cross-sectional area of a pipe, the flow rate in that pipe is going to stay the same. The flow rate is going to remain the same in a pipe. So if we had a pipe or a syringe that had something that looked like that, and there's water moving with some velocity and it has some radius, but now what happens is that pipe changes radius, which in fact changes the area, then what's going to happen to the volume? Well, the velocity is going to change. Because if we talk about location 1 and we talk about location 2, the flow rate at location 1 here, because there's only one place for this water to go, and it's that way, is going to be equal to the flow rate at location 2. So then if we take flow rate at 1 is equal to flow rate at 2, do a little bit of substitution, and instead of saying flow rate at 1, I can say A1 times V1. That's my flow rate.
Excuse this in at the day announcement. If you are a current sophomore or junior, please remember that you must have all of your course requests in by 4:30 p.m. tomorrow. Remember that you need a minimum of 52 units, and you must have 4 alternative courses selected. Please make sure you do that, or we will have to call you in on Friday during ELT. Thank you.
So if your flow rate here is equal to flow rate here, well, flow rate is A1 V1, or A times V, so A1 V1, and that's equal to flow rate here, A2 times V2. So then what we can do is we can say, well, if we had an A1, or if we had a V1 and an R1, we could calculate A1 and V1, and then we have like an R2 and we have a V2, then we could figure out one of those other ones. And that's what question number 5 is looking at. And I'll just read it, we'll kind of talk about it, we'll set it up tomorrow. So number 5 says water is flowing through a pipe with a velocity of 1.5 meters per second. So 1.5 meters per second over here. And it has a radius of 0.04 meters. If the pipe narrows to a radius of 0.02 meters, what is the velocity of that pipe, or of the water in that narrow section of pipe? What should be true? Is my velocity going to be faster or slower than 1.5 meters per second? Stick your thumb over the end of a hose, and what happens to the velocity? It's faster, right? Because it's moving faster, it should move further. But the amount of water coming out of that hose that you're spraying your little brother or sister with is equal to the amount of water moving through the bigger section of the hose. So why do they put a nozzle on a fire hose? To make it go faster, to make it go further. Okay? Why do they, you know, that's kind of that idea. I was gonna say, why do they change the size of the pipe in your house, but that's more volume than it is velocity. So we'll pick up that calculation tomorrow, and then we'll kind of be moving on. There's not a whole lot left to flow rate. It's just kind of using like this equation, the A1V1 equals A2V2, which is located, just for the record, right here on your formula sheet, right below flow rate, A1V1 equals A2V2. Just for the record. So that's a good stopping point. Have a wonderful Wednesday.